Okay, so I would like to start the science part of this mini workshop. So this is a collaboration between two grad students and two professors here at the university at the physics department, and we are trying to grow graphene on substrates such that we're going to be able to obtain completely epitaxial films, and to do that we use a set of techniques starting with scanning tunneling microscopy and electron diffraction. And essentially what I'm going to give you is an overview of the kind of results we're getting in the past couple of years. So what is exactly graphene? Professor Ijima has already introduced that. This is a nice, on the upper part here, this is a nice view graph of one sheet of carbon, that would be essentially one of the sheets of graphite that we call graphene. And this is a nice view graph of the atoms, using electron microscopy, of the atoms of carbon here. And what we would like to obtain here at our physics department is such a perfect sheet on a substrate. This is already an idea that has come out of a few researchers using silicon carbide and using thermal treatment of silicon carbide to obtain perfect sheets of graphene on top of it. So one of the questions, before we are sure that we get the graphene sheets, we should also know what are the defects and what is the structure that we are retaining. So we started to study these using a set of techniques that are available here at the physics department. And the essential questions that we wanted to answer are, what is the structure of graphene on silicon carbide, and is there a presence of defects on graphene, and does epitaxial graphene behave like a spholiated graphene, self-standing graphene? Silicon carbide has several possible structures, and we have tried to use essentially the 6H silicon carbide structure. And if we heat treat that to above, let's say 1200 centigrades, the silicon evaporates, and what we're left with are several sheets, or one or two or several sheets of carbon that have exactly the structure of graphene. The growth of this epitaxial graphene on silicon carbide, as I said, is done using silicon carbide substrates heated to a temperature above 1200 centigrades. And as this treatment is done, the silicon atoms evaporate and the carbon atoms form a reconstructed surface on top of silicon carbide. And the continuous evaporation of the silicon leads to the formation of graphene monolayers. For each more or less 3 bilayers of silicon carbide, 1 monolayer of graphene is formed. So we are able to control the formation of 1 to a few monolayers of graphene. And since the substrate is already crystalline, the idea is to obtain directly the epitaxial graphene on top of this substrate. And you can do this in UHP conditions, let's say 10 to the minus 10 core, or you can work in an argon atmosphere, for instance, such that we get an environment that will not contaminate the graphene once it's formed, and you have a very perfect graphene on top. So this is a view graph of of the mechanism of formation of the graphene film. You have the silicon carbide, you heat treat, then the silicon atoms absorb, and you start to have a graphene film which is reconstructed, and eventually you form more than 1 monolayer. And this on the right is the crystallography match of the graphene on top of the silicon carbide. And actually what we have is a supercell of graphene on top of silicon carbide. As I'm going to show, this is not a perfect graphene film. How do we follow the formation of this epitaxial graphene? What we use is low energy electron diffraction. What we get is, I'm not going to go into the details. What we have is an electron diffraction pattern from the substrate, and once you heat treat, you start to have first the formation of a reconstructed carbon surface on top, and eventually as you go along time and temperature, you start to have more a carbon reconstruction. Different one starts with a square root 3 rotated 30 degrees on top of the silicon carbide, and eventually you get more cumbersome reconstruction of graphene on top. And actually this is not graphene yet, this is only the carbon reconstructed on top of the silicon carbide, and eventually you get the graphene on top of the reconstructed carbon surface. And the next question is exactly what is the structure, and is this really graphene? So what we what we do is we do an STM analysis. And to do an analysis on a single sample, we decided to grow a sample with a temperature gradient, such that we will have in one sample we would be able to analyze the films with different thicknesses and different structures. So on one end of the sample, it was 1250 degrees Celsius, and on the other hand, this was 1450 degrees Celsius. And as you can see, the scanning microscopy measurement on one side and on the other is quite different. This is because of the reconstruction. This is not exactly a high-resolution scanning microscopy, but you can see the atoms here. I'm not going to go over all this in such a short time, but you can see the reconstruction, the supercell here, and eventually at much higher temperatures, you don't see the supercell anymore. What you're actually getting here is graphite, not graphene anymore. And if you do Raman spectroscopy of this, you see that this is a single layer, on a single layer, not epitaxial, but exfoliated graphene. You have a very sharp peak, meaning that you have only one layer of graphene. As we grow, as we do this analysis, this is not the same sample, but as you do analysis of the Raman spectroscopy of a single layer epitaxial graphene and two layer epitaxial graphene, you see that actually the graphene is attached, covalently bonded to the substrate, and is not going to behave like epitaxial as exfoliated graphene. So what else can we learn from this sample? Actually, what we decided to do is to do an X-ray diffraction analysis to understand the defects that are formed on this epitaxial graphene. So showing the two ends of the same sample, what we observe here is the several domains are formed, and actually these could be rotated domains with respect to the substrate. So in the beginning, the very beginning, where you have only a few graphene sheets, these are not actually our single domain. This is not a single domain graphene. And actually, if you do an X-ray diffraction, you see three peaks here coming from different origins. The first one is the epitaxial graphene, as everybody observes, but you also see two other peaks which can be associated to different carbon distances. One which would be shorter to the carbon distance of hexagons and of honeycombs, and the other one which is larger distances to this one. Actually, these results are, let's say, a year and a half old, and we were scratching our heads to understand what was happening here. I'll show the explanation in the next view graph. On the right, we actually see what happens at a much higher temperature. You see these much larger domains performing essentially highly oriented with graphite. And if you do the diffraction, this is what actually you see. You see a single peak exactly showing that you have formed epitaxial multi-layer graphene, if you will, instead of graphite. Okay, anyhow, what is the explanation for these two diffraction peaks that we see here? Actually, a month ago, there has been published a paper on this, showing that actually you can form defects. You form defects on epitaxial graphene, where you see not only these hexagons, typical hexagons of graphene, but you see heptagons and pentagons. And actually what we're seeing there is the signature of the distances of carbon that is changing from the typical 6 hexagon distance to the 5-fold and the 7-fold cells that you can form. So actually epitaxial graphene does have this kind of defects, as well as other kinds of materials such as nanotubes or so. So another project that we have been involved is the work of epitaxial graphene on argon pressure. In this case, the results that we get are actually quite different. What we get from the Raman spectroscopy is that the kind of widths that we get from the Raman result are almost exactly the same as exfoliated graphene. Even if we grow several layers of graphene, as I showed here with the microscopy, we actually observe that the behavior of these sheets are of a single layer. So what we're actually synthesizing here are several layers of graphene. So it's a multi-layer graphene that actually does have a behavior of a single layer graphene. And if you do an analysis as a function of time, you see that the peak does not change its width, and at the same time, with the diffraction, we observe that we were actually synthesizing several monolayers, up to 30 to 40 monolayers of graphene. With diffraction here, the peak is getting narrower and narrower, showing that you have actually more and more layers of graphene, but the Raman spectrum does not change. This shows that we're actually synthesizing several monolayers of a single sheet of carbon with the behavior of a single sheet of carbon. So the conclusions in this very short time that I would like to show is that actually it's possible to grow epitaxial graphene, but it does not behave like spalated graphene, not in the case of ultra-high vacuum. That in scanning thermal microscopy shows that we have obtained graphene domains and with different carbon distances. And the explanation for that would be that we actually have pentagons and epitagons being formed to accommodate the stress imposed by the silicon carbon substrate. In another project of another student, we actually have been able to synthesize multilayer graphene under argon atmosphere, and the then Raman spectrum shows that actually this multilayer graphene behaves like a spoliated graphene.
Okay, what makes this your multi-layer different from a multi-layer graphene? Why do you think you have a lot of single layers on top of each other, and why is that different from multi-layer graphene? What's the explanation for that?
So actually, there should be some kind of interaction between layers. If there's if there's a relaxation mechanism, a formal relaxation mechanism between one layer and another one, you should see a broadening of the Raman spectrum. Okay? So if you have a very narrow one, this means that once you have, I'm not an expert on Raman scattering, but if you don't have more than one mechanism of relaxation, you would not see a shift in the peak position such that you will have a single peak. If you have a single peak, then you actually have one single layer. That's all. They don't communicate.
Do you see any differences, two types of one-on-one surface, silicon carbon?
Yes, but it's very preliminary still, so I would not like to comment on that because I would be too bold, I would say.
Thank you.